Dark humor. Yes. All right. So
Don't get me started with dark humor.
waves.
How do you make a baby float?
Oh no! Please, please.
Move your leg up its head.
Oh, Andrew. No, stop, please, please. Stop. Keep these tasteless jokes for after class, please. Right, reflection, diffraction, refraction.
Again?
Reflection, diffraction, refraction. Okay.
This is in the coffee.
No, kitchen. I'm making the kitchen.
No, but the cup.
Yeah, I think so. There's 3 cups in the kitchen. Free. And the
Which
tea is
kitchen?
free.
Yeah.
It's staff kitchen.
Oh, makes sense.
Yes. Okay, you got that? Yes? Yep. Good. So there's a lot to do in this lesson. We might have to split it into 2 halves, but that's okay because I still think we're doing pretty well. There's 3 lessons left. We have classes this week. We have one class tomorrow, so we'll certainly get this finished with the homework tomorrow. And then next week we have 6 hours.
You said tomorrow is the 1 hour assignment?
Oh, that's right. Okay, then we get this finished next week then. Yeah, so we'll work on the assignments tomorrow then. Okay. We have, so we might have a chance to get in a practice test at the end then. Okay. So, definition, reflection. What is reflection then? We know this word from day-to-day life.
No.
We don't? Okay.
Reflected ray is equal to the incident ray.
Yeah, but break it down a bit more. It's the change in direction of a wave at a boundary between 2 different media, so as the wave moves back into the medium it came from. The most common examples are reflection of light against a mirror, sound against a wall as well actually, when you hear an echo. Yeah, reflection. Okay. So we have 3 definitions, please write them down. The first one we will do is reflection. You don't need to write the most common example, you just need to write the first sentence to hear.
Sorry? When we use this different, when we use another different.
What?
When we use this,
Different.
yeah, and another different.
Another different. What's it?
DFF.
There's different and difference.
Yeah, when.
Yes.
Between 2 different media?
Yes. I think the difference is, let me think.
And mirror. You know a mirror? You see
Different is an adjective, different is a noun.
No, it's bottom.
Is it really?
No.
Actually,
Hey guys, grammar moment. Fawn was looking for the difference between different and difference. So I was thinking different is an adjective and difference is a noun.
Yes.
Yeah. So you could have like different media, different person, different time. That's an adjective. And then difference. What is the difference?
When you say difference, you have to speak about 2 or more things.
Yeah.
Change between things.
Change between things, yeah. But different could just mean something else.
It's media.
Media is the
I'm different. Yes, I'm different.
Yes. Hold on.
don't confuse me. Media plural, medium is singular. Yeah. Okay, you got this? No. Can I write?
yeah.
Where? Here? Okay. Different. difference.
Where is the price that I gave you?
This one is an adjective. Yeah, and this one is a noun. So an example, different time, different person. So a different person means someone else. A different time means another time. But difference is a noun, so you could say something like, what is the difference between him and her?
It's also the difference.
Yeah.
Yeah.
Yeah, it is, yeah.
So different.
But you don't say different time, different person. When you're using it as an adjective, you say different. And when you're using it as a noun, you say different. So it's the same. It's like the same word. Adjective you use with the T, and noun you don't.
Yeah.
So what would you say? Like, give me a something pen. Give me a different pen. Give me a different pen.
Oh, so it's a noun.
Yeah. So give me a. Yeah, no, but pen is the noun.
Oh,
So it's an adjective on the pen. Different pen. So it's an adjective. Good.
so adjective is before the noun.
Yes. Yes.
But what happens if after the noun?
Doesn't make sense. You can't say pen different. It doesn't make sense. It's like saying boy fat. No. It's
So here's the real question.
Fat
Can you grow a
boy.
beard?
Oh,
We'll say later. Guys, please. I'm trying to do some grammar here. Right, next. Diffraction. So, diffraction is when the wave bends around small obstacles, or when it spreads out. Here's a good picture to show you diffraction. This sound wave, or water wave, spreads out more when the hole is smaller. In other words, we can say here there's more diffraction, here there's less diffraction. So often diffraction is used to mean the spreading out of a wave as it passes through a small opening.
Is it small or is it equal to the wavelength?
I know, it could be smaller or larger than the wavelength. If you want to have a noticeable diffraction, it should be on the same size as the wavelength, yes. But as far as I can think right now, the smaller the hole is, the more diffraction there should be. But you won't really get any diffraction if it's bigger than the wavelength. But you still will get some.
Only at the edges.
Yeah, like in this picture. Okay, did you write this definition down? Yes, continue. Okay. Pass through small opening. Yes, continuing. Yusuf, yeah, okay. So the next one now is refraction, and that's the change in the direction caused by change in the wave's speed. Refraction is seen most often when a wave passes through from one medium to a different medium. Here is a good example. So here is air, here is glass, and here is air. The light changes its direction as it moves from air to glass. Then, as it moves from glass to air, it changes the direction again. This is called refraction.
Would laser be counted as light waves,
Yeah.
not light rays?
We don't distinguish the word so much. You wrote this down wrong?
No.
Yusuf? Yeah. Why are they so fast? Because they're so smart.
Will we do total internal reflection?
Okay, you got that now?
No.
No. What are we waiting for?
We leave one man behind. That's
We
what
do.
they told us.
Are we only waiting for one? And we're waiting for this guy too. You're done. All right, side wrong.
Wait.
I'll give you.
Different
I'll give you one sip of tea. Okay, continuing now. Some materials will allow light to pass through them more freely than others. So, a material like glass will allow the light to travel through it easier than maybe
Wood.
yeah, wood. So, where some materials will slow the light down. So as we were saying earlier, when the light travels through the air from the sun, it's slowed down. For example, light moves slower in gas than in glass than in air. The refractive index is a way to measure how fast the light can travel through the material. So the definition is, the refractive index of the material is the speed of light in a vacuum over the speed of light in the material. This is the definition of the refractive index of a material.
Can we measure the speed of light, or we can only calculate it through the formula?
We can measure it. You will learn how in ESAP.
We did.
Did you do that video lesson?
No. No, we
Yes?
didn't.
You had a video? Yeah, but then you did learn.
We didn't do any video
We did.
about light.
You were sleeping.
Oh, the thingy, the ratchet that moves. Okay.
See?
Yeah, measuring the time, and they know the distance. So time and distance. Okay. That was the way for me to see.
It's like the person who designed the ESAP lessons knew something about physics.
True.
Yeah. Okay, did you get this definition?
Did you say that C is the speed
In a vacuum, light in a vacuum.
You said it's the speed of electromagnetic.
Yeah. In this context, we're talking about light. Now, if we look at the n carefully, will it be bigger than or now think carefully? Will it be bigger or smaller than 1?
Always bigger.
Smaller.
Always smaller.
Always bigger.
Smaller than
Look at it. Is the V bigger or smaller than C?
Smaller.
Smaller. So you have
So
a.
how can it be less than 1 if it's smaller than?
Hang on. Hang on. So is it going to be bigger or less than 1? You're going with more than 1, and you're going with.
More than 1.
I thought you were saying less than 1 a moment
No,
ago.
I said more than 1. He was saying less
Okay,
than 1.
okay. So look, for example, maybe the C is 3 times 10 to the 8 and the V is only 2.99 times 10 to the 8.
Is that possible?
Yes, it's slowed down slightly.
Yeah.
So you have a number which is a little bit bigger than 1. In fact, what would happen when n is equal to 1? What are you saying?
No refraction.
No.
Same medium.
Yeah, well, it's also a vacuum. The light is not slowed down because the V and the C are the same. So, in other words, the bigger the n, the more the light is slowed down. So n can be from 1 to infinity. 1 is a vacuum, which is not interesting because the whole reason we have this is because it is slowed down. And infinity means the light has completely stopped moving because the V will be 0. Not something we'll deal with. it's not really possible to slow light down until it's not moving, but the record, I believe, is a special glass that can slow light down to 1 meter per second. Yes.
Glass?
Yes, a special type of glass.
So you can put the glass and run and
Yes.
it will reach the
Yes.
edge of the light?
Yes. So 1 meter per second is the slowest. So this means it has a huge refractive index.
Do you have the
Huge.
name of this glass?
No, but if you Google things like slowing light down to 1 meter per second, I'm sure you can get the YouTube video for it.
And so you can use the light here.
Yes! Which is amazing. It's amazing. I thought you might like it. So you can try and get this on YouTube later, and you can see the light move through the material.
I'm moving faster than light.
Yes. Technically true. Okay. So, remember B equals C only in a vacuum.
Take a video of you running. How cool is that?
Every day I run
Slow
faster
motion,
than
pretend slow motion.
Every day I run faster.
You can do it like flash style.
Yes.
Yeah. Right, so we have a new law called Snell's law, and Snell's law lets us calculate the angles for refraction. So what happens here is you have a material with refractive index N1, you have another material with refractive index N2. The wave comes in and it hits the material. This could be like air and this could be like water, for example, and it will change direction. Let me put it something like this. So this line here is called the normal. It's perpendicular to the surface, and this angle here we can call it I or θ1, whichever you prefer, and then here is the new angle afterwards, or θ2 if you prefer. And we want to know how can we calculate, for example, this angle if we know this angle. In other words, we want to know how the angle changes. So Snell's law is a way to relate the angles. Basically, if I call this θ1 and this θ2, sine θ1 over sine θ2 equals n2 over n1. This is how we can calculate angles of refraction. So θ1 on the top, θ2 on the bottom with the normal.
We have to go over.
I know.
Sin I over sin R.
Sine I over sine R equals n2 over n1. Okay, now that's one form of it. Another form, okay, so I've just wrote down what they are, but I drew you the picture as well. And here's the picture here as well. θ1, θ2, n1, n2. Also, the velocity changes. For example, if the light is going from air to water, will the light go faster or slower? Slower. So you could also produce the formula using the velocities as well, as another example. So we have different ways to write Snell's law. Let's look at the other forms of it now. Can I continue? Okay. So other forms, actually just before the other forms, in certain conditions it's possible to choose an angle, which we'll call C, so that the refracted angle is 90. This is called the critical angle, and let's find the formula for that. So what's happening here is we have a material, and let's say this could be some type of glass, and maybe this is a different type of glass or whatever, it doesn't matter. Yeah, I won't do the water one just yet, N1 and N2. So it's possible to find an angle so that the light actually refracts across the surface. And if you try to increase your angle past this, it actually comes back to you. Yeah, reflect.
And if it's
and refracts, yeah. So this is called a critical angle. Let's calculate it. Sine I, or sine theta 1, what's theta 1 here? C, over sine theta 2, and what's theta 2 here? 90, equals N2 over N1. What's sine 90 though? 1. So you get C equals sine inverse N2 over N1. So for this to work, this can only work if N2 is smaller than N1. Because if you try to do it the other way, watch what happens. If you do sine inverse a big number over a small number, you get an error. You can only calculate it, and it only works if you have a small number over a big number. So in other words, you have a critical angle only in this situation where N2 is smaller than N1. This is the formula. Yeah.
Can we go back to the definition?
Yeah. Not really a definition, but just the idea. So when this happens, when the light returns to you, it's called internal refraction. So we don't call it reflection because it's a special situation. We call it internal refraction. Okay, you have this?
Mm-hmm.
Yeah.
Yeah.
No. Well, I would like you to write down that word, internal refraction. Internal refraction is this when it comes back to you. Yeah, you have that? Internal refraction is this when it comes back to you. You have this? Can I continue? Yes? Okay. So, notice in the last lesson you did not see a frequency or a wavelength for white light. That's because there is no frequency for white light. White light is actually just all the colours added together. So we have frequency for red, orange, green and so on, but none for white. That's because white is a mixture of all the colours. So that is, if you take red light, orange light, green light, etc., and you just fire them all together, the colour you get at the end is white. So, yeah?
We mix the colors. We have all the different colors.
Yeah, you get white.
Cancel.
No, that's a different thing. That's different. You get black then in that one. So, yeah?
And you have this frequency for all the colors.
No, just that you have many frequencies. There's many different ones. Yeah.
As it goes together.
The frequencies don't add. Yeah, they stay separated. You just have many of them. That's all. Like a collection of them. So white light is just all of them mixed together. Okay. Another way to state Snell's law is by using the wavelengths. So you could say sine theta 1 over sine theta 2. Yes?
Do we have black light?
No. There's no such thing as black light. You can have black surfaces, but not black light. Another way to state Snell's law is sine theta 1 over sine theta 2 equals wavelength 1 over wavelength 2. Therefore, light of different wavelengths will refract differently. This is why white light, which has all the different frequency, will produce a rainbow. So what's happening here? White light is all the different wavelengths. Which ones have the biggest angles here of refraction? Now, you just have to be a bit careful here.
Refraction?
Yeah, just remember, we measure the angle with the normal.
Yeah.
So, if this is the surface, and this is the light coming out, we measure it to the normal. So this is one angle, but if it's going like this, it's a bigger angle. So which ones have the biggest angle here?
The bottom.
The ones at the bottom,
Right.
the violet ones. Yeah? And the ones with the smallest angles,
Right.
the ones at the top here. So the reasons they get refracted differently is because they have different wavelengths or different frequencies, which causes them to have different angles then. Different angles we're focusing on. So this is why a prism splits the white light into different colours, because it's forcing the light to refract, and the different wavelengths then appear to be refracted differently by using Snell's law. So this is the maths, the physics behind how we get the rainbow colour from the white light. I would like you to draw this diagram, please.
Why did they always use a prism, not just a normal lens or normal glass?
It's probably the most efficient way to split the light, having a flat surface.
Yeah, but the glass is also flat.
I don't know, ask Newton. He's the one who did it.
Is there not a reason for it?
I just think maybe it could even be as simple as the fact that prisms are cheaper because you don't have to curve the surface. It's just a triangular piece of glass. Any idiot could make that, you know. But making a glass or a lens requires actual skill. Okay, you have this.
Does that mean that the red light is like the heaviest?
Heaviest, we wouldn't use this word, what do you mean?
Like, well, why is the red the least refractive?
Slowest.
Yes, no, not the slowest. It's each color has a different wavelength and frequency, and different wavelengths and frequencies will result in different refraction. Here are the three ways you can state Snell's law. The first one we've done, using the refractive index of the materials. The second one is looking at the wavelengths of the waves before and after they're refracted. And the third way is to look at the velocities before and after refraction. Just take care here, this is 1, 2, this is 1, 2, but the first one is 2, 1. That's not a mistake, it is that way around. Please take care of the ones and the twos. Continue? Yes? Yeah? Sorry, do you have this? Yeah?
So one has to be bigger than 2 and
No, that was only for critical angles. It can be anything, but if we want a critical angle, it needs to be. Right. One use of Snell's law is actually in making lenses. When light enters a glass, it will refract. But if the lens is curved, the result is different angles. If you can make the lens carefully enough, you can cause the refraction to converge. So I'll explain here with my picture. So you know, if light comes in at one angle, there's θ1, it could refract and come off at a different angle. If you curve the lens, what you can try to do is curve it so that when the light comes in and refracts, you have it designed so that it refracts and all meets at one point. So this is quite difficult to do. You have to have the lens specially curved so that all the angles you get here are the right angles at the right places so that the light converges at one point. So it's very difficult to do. You know, it's requires careful calculations and careful smoothing of the lens. But if it's done right, then all the light that's refracted will refract and meet at one point. This is the idea behind lenses. In fact, all the lens is doing is refracting the light in a special way to cause it to converge and meet at one point. So this is one application of refraction, is to make lenses. You can just even write that down, that an application of refraction is making a lens.
Sorry?
Yes.
So if the person who wear lens, if he see the
Yeah, it might burn his eyes out. Oh, really? Yeah.
more than normal.
More than normal, yes. So definitely don't do this. Okay, so just write down refraction application is lenses. You got this, Andrew?
This?
Yeah? I mean, did you write that down? Okay. You don't want to?
No, I'm trying to figure out which part I should write down.
Oh, what I just said. Unless you want to do your own thing. So one application of refraction is making lenses. Okay, continue. So, we have a question and then we have homework. So what we can do, when's our next class? Tuesday? No, but, well, I mean, we're using that for coursework. So Tuesday, we can do this example and these questions in class on Tuesday. Then, is it double class? Yeah, and then we'll do interference. And then Wednesday we have a double class, a single class, we'll get that finished, and then Thursday is a double class, we'll get that finished. We'll get this finished next week, and do we have classes the following week?
Yeah.
Perfect. So then in that week we'll do revision and practice test. Sounds like I had this planned perfectly, which I